let's go over your discrete random variables warm up for the quiz that you're going to be having. So this kind of summarizes all the types of things that you needed to know in our discrete random variables section. All right, so here we were actually given this relationship of the number of emails that the professor receives and then the probability of receiving that many emails. Okay, now you were first asked to give the how many emails should this professor expect to receive? So that's the expected value, that's the mean, and with what standard deviation. So you need to show this work here. 0 times the 0.05 plus, and then you can do the sequence since the table is shown to the top one, 5 times 0.10. So on average, this professor is going to have about 2.95 emails whenever he gets to school in the morning that he needs to address with this variability. This is the x minus the mean we just calculated, quantity squared times the probability, and then plus dot 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 up to the last in the sequence, which is 5 minus the mean quantity squared times that probability. So the variability is 1.32 emails. All right, now we are asked to transform from number of emails into how many minutes that will take him. So we are told that it takes the professor 2 minutes to respond to each email. So, how much time should that professor expect to allot for himself when he's starting up in the morning to respond to student emails? So, again, we're transforming. So, that follows the transforming rules. So, this is just multiplication. So, 2 times the mean is at 5.9 minutes on average. Context. You need to include the labels on these. I will take off if you do not include the labels. That is actually in the AP objectives that students are including the labels of these events. Okay, so the standard deviation is 2 times the 1.32 minutes, so 2 times 0.64. Now, take a look at what happens next. Now we're going to have an addition component where we are adding 3 minutes to boot up the computer and get logged in. And so, how is that going to affect our time that it takes him to get going? So, the mean is affected by that adding of 3 minutes. So, it's now 8.9 minutes if he wants to boot up his computer and get going in the morning. But the variability stayed the same. Standard deviation was not affected by the plus 3. All right. Now, assuming the distribution of the times that it takes the professor to turn on the computer and answer emails. So that actually is important. It's the turning on the computer and answering emails. That indicates to me that I'm going to use the mean and standard deviation from parts D and E, not from parts B and C. All right, so I went ahead and drew out a picture of this, and we want to know the probability that he takes no more than 15 minutes. So that's 15 minutes or less. So again, with a mean of 8.9, and so then I want to find the z-score at that spot is 15 minus the mean over the standard deviation, 2.31. So 98.96% of the time, he will spend no more than 15 minutes turning on his computer and answering his emails. All right. Here we go. Next. Okay, so this is now a combining problem where we are adding together yearly costs for a dog and a cat. And I believe we're doing one dog and one cat in this problem. So I just wrote the summary statistics up here with the one dog and one cat, mean and standard deviation, and the uh, for the yearly costs. Okay. So the first question, what's the expected value for a person who has one dog and one cat? So this is a combining random variables problem. So I'm adding those two means together But the standard deviations do not just add, they combine to go through the Pythagorean theorem of statistics. So there's that's 30 squared plus 35 squared, square root it. All right, what's the probability then? So I'm going to use that mean and standard deviation, the probability that a person will spend $240 or less veterinary care for the total cost of a dog and a cat. So I used that mean and standard deviation, and I figured out the 240x minus the mean over the standard deviation, and I norm CDF'd to get that area. So just there's only a 4.09% chance that that person's going to spend $240 less. So they probably should budget more than spending $240 on their dog and cat. But what's the difference? So how much more do they expect one of them to be than the other? I chose to do dog minus cat because that would have given me positive numbers. You could have done the other way around. Um, and so then here's an important fact. Remember, this was one of our special things that we demonstrated with the cereal boxes, that even if you're finding the difference between two variables, the variability gets bigger. So this standard deviation for their differences is not smaller. It is identical to what we came up with in part B. All right. Now then, we're going to ask a question about that. If the difference in cost can be described as the normal model, what's the probability that the medical expenses are higher for someone's cat than the dog? So the way that I did this was I first started off with my normal model. I drew it out here. And so, okay, got it. This was a negative 12. Okay, so I know on average, so define, make sure you are clear on which way you are subtracting. So I'm subtracting dog minus cat, and there's my 80. Okay, and then the place where their difference is 0 is where their costs are the same. Okay, so then I need to define what's happening on each side of this line of equality. And so I know to the right, the first number, the first variable, dog, is more than the cat. So over here to the right is the proportion of times that the dog cost more than the cat. And then the opposite is true to the left. The left is the proportion of times that the cat costs more than the dog. So once I have identified the location of what's happening there, I'm now going to go answer my question. They want higher for the cat than the dog. Okay, so then I know, okay, that's here on the left. So I'm going to norm CDF, that 0 minus the mean over the standard deviation, and then do that area below that, which was 4.09%. Interesting that it was that there. Okay, moving on to the next page. So this, I actually looked up this information, but here we now are doing several dogs and several cats. So on this page, this problem I wanted to see, are you able to combine, transform and combine? I guess here, luckily, they've already transformed into cost. Okay, so the cost is already there. But we have multiple dogs and multiple cats, not just one. So how are we going to handle that? Well, there are 3 cats and 2 dogs. Wrong. 3 dogs and 2 cats. So I'm combining those together. Wow. So that person needs to budget a lot for their animals. With what standard deviation? So there are 3 of the dog standard deviations squared plus 2 of the cat standard deviations squared, and then we square root that. So there's the variability for the cost of those animals. So they're going to budget $4,000. Okay, so they're going to budget $4,000 yearly. Okay, good thing because that's a lot. Wow, what is that? over 380 $75 or whatever a month. Wow. Okay. They love their animals. So we're going to then see what's the probability that this family is going to go over that $4,000. Okay. Well, we know the average is 3,625, and so going over that 4,000 is that x minus mean over standard deviation, and then there's how we get that top 6.55%. All right, this next one was an actual AP question. It was a free response question, number 3 in 2015. Okay, so here we go. What is the probability that at least one ATM is working when the mall opens? Okay, at least one. So I'm going to add together these probabilities for the 1, 2, and the 3. And there that is. If you were to write the probability notation, which is always a bonus because it always just feels so naked to me to write equals this number. Okay, but anyway, next, what is the expected value for the number of ATMs that are working when the mall opens? So there was only 4 values there. And with this being an actual AP question, I was kind of thinking to myself, I'm going to be good and write them all out and not just write out the sequence. So you might consider that on the actual AP. If it's reasonable, just go ahead and write it all out. So there's just no question. So I did that. I wrote the x times this probability. Oh, there's supposed to be a plus sign right there. Plus that x times that probability, and so on. Okay, and so that came out to about 1.73 on average. They didn't ask for the standard deviation, so that was nice. What's the probability that all 3 ATMs are working when the mall opens, given that at least one of them is working? Ooh, that's interesting. That is a throwback to before Christmas, our Unit 5. Find the probability that 3 are working, given that at least one of them is working. So this bottom part is actually what I got in part A. And then the top part, of course, is the 3, the 0.24. So if at least one of them is working, then there's a 28% chance that 3 of them are working. All right. But now this next one takes some thinking. Take a look at this. Given that at least one of them is working, when the mall opens, would the expected number, so see this expected value here of the number, would this expected number be less than, equal to, or greater than what you got in part B? Explain. So this one's kind of a hard one to think about. I mean, I don't know. It may not be hard for you, but I think I had trouble kind of verbalizing it to be able to explain it. So I think that they gave you this part C question so that you could do part D. Do you see how the probability that in part C, the probability that 3 are working is 0.24. But in part C, if I knew at least one of them was working, then that probability went up. And the reason that the probability that 3 went up is because now we're talking out of 85%. See, we're talking about out of this denominator, what's the probability of that happening? The same idea is happening with part D. Therefore, what's the expected value given that at least that one of them is working? So then what happens is this. Our new mean is, here's how many we expect to be working out of the 0.85 chance that at least one of them is working. So that expected number is going to be greater because we already know that at least one of them is working. So see, we don't have to account for that zero part. That would happen because the probabilities are recalibrated then out of 85%, and so that at least one of them is working. So we would have recalibration out of the 85%. All right. So that's what you had to go through to explain that. So it was greater than, and it's because it's out of the 85% instead of out of the total. All right. I hope that that warm up is getting you ready for your quiz that you will have tomorrow on discrete random variables.